Good morning, everyone. Today we will start with chapter 5 about the laws of motion. So you remember in chapters 2 and 4 previously, we were studying kinematics, and we said that in the kinematics we are going to study and describe the motion of the objects using variables or parameters such as position, velocity, acceleration, speed, etc. And we discussed the case of an object moving under constant acceleration, where we derived the kinematic equations for it. We also have seen that an object could be moving under constant velocity, and we have seen what also the kinematic equation that is corresponding to this case. We also have seen the two-dimensional and three-dimensional motion, in particular the curvilinear motion, circular motion, and uniform circular motion, and what are the acceleration that we define for this kind of particular motion. However, in all our discussion, we never come to the insights to what caused the motion, why we have the motion, why we have the object accelerating or not accelerating, etc. So all these questions, we will answer them in the dynamics. So in this case, we are going to study the factors that have produced the motion or have changed the motion of a given object. And the ground basis for this would be the laws of motion formulated by Newton, where actually we're going to introduce two new concepts to study this, what causes the motion. First of all, the forces usually acting on a given object, and the mass of an object. So this dynamics will be the topic, will be the task of both chapters 5 and 6. Before to start and to introduce Newton's laws and the statement of these laws, we're going just to stop on one important point. When Newton's laws fail. So in principle, we can apply Newton's laws in general case. So we are here, look at this picture. In this picture, you have two axes. So the horizontal axis, it represents the speed of an object. So at the beginning of the axis, you are moving at low speed, like for example, any person, on a bike or a car, for example, or projectile, anything, ball. And at the end of, so we are going in the this direction. The speed becomes higher and higher up to the level where it's compared to the speed of light, which is very high speed. And on the vertical axis in here, we are going from very large object to very small objects. So objects from the size of a galaxy to the size of the atom. So where we are in this case here. When we say that we're going to study objects like, for example, a car moving on a road, a ball that is shot by someone, an object that is pulled or pushed by someone else, etc. We are in the case where we have objects that are big enough compared to the size of electrons or atoms, and that are moving at very low speed compared to the speed of light. When these two conditions, they are not respected, then we say that we cannot apply Newton's laws. So in other words, لما يكون سرعة الأوبجكت اللي عم نشتغل عليه كبيرة كتير وتقارن بسرعة الضوء, then in this case ما فينا نستخدم نيوتن's law. ولما يكون الأوبجكت اللي نحن عم نعمله study very small, very small, يعني بحجم electrons or atoms, كمان بهالحالة we cannot apply Newton's laws. Newton's laws can only be applied when we are dealing with objects big enough compared to the size of electrons and moving at low speed compared to the speed of light in the vacuum, which is 3 times 10 to the power 8 meters per second. Okay, so, and in general, we are going only to deal with this case where we have objects that are big enough and moving at low speed. Okay, otherwise we will be in different fields in physics, which is relativistic mechanics or quantum mechanics. And this we are not going to study. So let's start with Newton's first law. Newton's first law of motion states the following: an object at rest remains at rest, and an object in motion continues in motion with constant velocity unless it experiences a net external force. two comments before to discuss this statement. So first of all, this law is usually called law of inertia, and it defines a special set of reference frames called inertial frames. So actually, a reference frame in general is an X, Y, and Z system that is associated to a physical object, like associated to the earth, associated to a table, etc. So if we have a reference frame, where this Newton's law is valid, is applicable, that means that we are in an inertial frame. We call it an inertial frame. So when we say that it defines a special set of reference frames called inertial frames, we mean that wherever we have a reference frame where Newton's law is valid, we call it inertial frame. Now let's comment a little bit about this Newton's law. An alternative statement of Newton's first law, it means that in the absence of external forces, okay, when viewed from an inertial reference frame, an object, if it is at rest, it remains at rest, and if it is in motion, it continues in motion with a constant velocity. And this Newton's first law introduces, actually introduces a new concept, which is the force you see here. It says, unless it experiences a net external force. So this is number one. Here we introduce the force concept. And the Newton's first law, it states that when no force acts on an object, the acceleration of this object is zero, so that if it is moving with a given velocity, the velocity does not change. And be careful, Newton's first law, it describes what happens in the absence of forces. So we don't have any force that is acting on the object. And it does not describe zero net force. So when you have forces acting on an object, even if the summation of all these forces is equal to zero, we are not anymore in the Newton's first law case. And we can also conclude from Newton's first law is that any isolated object is either at rest or moving at constant velocity. And by isolated, of course, we mean an object that is not under net force. So the first law, finally, it allows the definition of force, as we earlier said, as that reason which causes a change in the motion of an object. So it says that if an object is at rest, it remains at rest unless you have a force that is acting on it. And if it is moving with a velocity, a given velocity v, it will continue moving with the same velocity unless there is a force acting on this object. So what is the force in general? Actually, a force is defined as that mathematical object that describes the interaction that causes a deformation or a change in the motion of an object. So what is this factor, because of which the object has changed its motion or has gone into a deformation, etc. This is what we call the force. Qualitatively, the presence of a force is the reason we give for the acceleration of the object. And that is a consequence of the Newton's first law, because the Newton's first law tells us that unless you have a force, you have an acceleration. You have to know also that the force is a vector quantity. So for example, if you are pulling some object, the force is in the same direction as you are pulling the object in, and so it has a direction, and of course it has a magnitude, which is the intensity by which we are moving or we are pulling this object. And of course the forces are in everyday experience. Like if we push an object to move it, we throw or kick a ball, we may push an object also and we're not able to move it. So all these examples, they involve force. We have two types of forces that exist. So first of all, we have the contact force. And when we say contact force, we mean that we have a physical contact that is involved between the interacting objects. Like in this case here, the first row, in all these forces, there is a contact between the body, for example, in our case, this is the hand, and the spring, between the hand and the cord, between this guy and the ball, etc. So this kind of forces are called contact forces. And we have also what we call the force at distance. And in this kind of forces, they act through empty space. So there is no need for a physical contact between the interacting objects. Like in this case, for example, the gravitational force between the masses. If you have two electric charges, also the force between them is a force at distance, a magnetic force, etc. Okay. So these are the classes of forces as seen in our case in classical mechanics. But in the general case, when we talk about forces in the universe, we have actually four fundamental forces, and all of them, they are field forces, so forces at distance. So we have the gravitational force, which acts between objects that having mass, like in this case. Whenever you have two objects with mass different than zero, then you can talk about gravitational force. Electromagnetic force, which acts between electric charges, like in this case, you have two charges, so definitely you have electromagnetic force between them. You have a nuclear force, which is the force that acts between the subatomic particles, like in this case, you have a proton inside inside a nucleus. So in this case, we talk about the nuclear force, and the weak force is the fourth fundamental interaction in the universe, and actually it arises in certain radioactive decay processes. So I don't have an example here, but in general, it's related to the decay of particles. So in our case, and here we're going mostly to deal with the gravitational force. The other forces we're not going to discuss. So we have introduced the mass, which is the first concept we talked about. Now let's introduce the mass. Actually, the mass is defined as the property of an object that specifies how much resistance an object exhibits to changes in its velocity. In other words, if you have an object that is moving with a given velocity and you apply a force on this object trying to accelerate it or decelerate it, it can be in both sides, the resistance of this object to remain at the same constant velocity it is moving with, it is defined as the mass. And you have to be careful about the notion of mass. The mass is an intrinsic characteristic of an object. It's just like the charge, electric charge, for example. So it's intrinsic of an object, a characteristic of an object. It's independent of the object's surrounding. So wherever the object is placed, the mass is the same, it does not change. It's a scalar quantity, which means that it's a number. And of course, the unit, SI unit of the mass is the kilogram. Let's now, after we have defined and introduced the mass and the force, see what is this Newton's second law statement. So when viewed from an inertial frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So we can write it in this way in terms of mathematical equation. The acceleration is proportional to the net force acting on it, so the summation of all possible forces acting on an object, and inversely proportional to its mass, so in this way. So we can write down sum of the forces is proportional to m times a, but the Newton's second law, it is given by this expression in here, sum of F equals to ma, where we have the proportionality constant in this equation is equals 1. So Newton's second law that you should apply and we should know is sum of external forces equal to mass times the acceleration. And you can see from here is that the force is the cause of changes in motion as measured by the acceleration. You have to remember something, an object can have motion in the absence of forces. So you don't necessarily have to have a force so that an object move. It can move without having a force acting on it. And you should not interpret force as the cause of motion, but you should interpret it as the cause of motion modification. If you have a force, then the state of the object will change. If it is at rest, it will start moving. And if it is moving with a constant velocity, it will change the velocity and will have an acceleration. So this is the way we understand the force according to Newton's second law given by the sum of external forces equal to ma. More about Newton's second law. So this sum of forces, it includes all the forces acting on a given object. Let's take this example. You have a given object here and you have three persons that are pulling this object. So we have three forces, Fa, Fc, and Fp. Now, what we say that F net, the net forces acting on this object is defined as the vector sum of all the forces. So it's Fa plus Fb plus Fc. And whenever you want to apply Newton's second law on this object to study it, then you can say sum of external forces equal to ma. You have all the forces. You should define your reference frame. So you should always define x and y axis in order to make the projection of these forces along the axis. And so the Newton's second law, it becomes a set of three equations. So the projection along x, projection along y, and the projection along the z. So sum of fx equals max, sum fy equals may, and sum fz equals maz. Now the gravitational force. Let's introduce the gravitational force. The gravitational force, actually, it's nothing else than the force that the Earth exerts on any object on top of it. So all the objects that are present and they are located on the surface of the Earth, they are subject to the gravitational force. And this force, it's directed all the time towards the center of the Earth. And its magnitude, it's given by a Newton's second law. So let's see how can we get its magnitude. If we consider, this object here on the surface, so near the surface of the Earth. Okay, this object, if no other force is acting on the object except the gravitational force, then we can say that this force is under Fg, where Fg is the force exerted by the Earth, and it is pulling the object downward. So Fg, according to Newton's second law, is equal to ma. Okay, but in this case, A is nothing else than the gravity acceleration g, as we have seen earlier. So it's minus g I, where I is unit vector of this y-axis. And so we can deduce from here that the modulus of this Fg, the gravitational force, is nothing else than m times g, where m is the mass and g is the gravity acceleration that we have earlier studied in chapters 2 and 4. Now the weight of an object is equal to the magnitude of the gravitational force exerted on the object, okay? We call it sometimes W, or we call it Fg, it doesn't matter. In the problems, I will all the time use mg itself. So the weight of an object is not its mass, be careful. If you have an object that is moving actually near the surface of the Earth, then we know that the gravitational acceleration is 9.8 meters per second squared. If this object goes beyond and far from the surface of the Earth, then the gravity acceleration, it becomes different than 9.8 meters per second squared, as we have seen in the previous chapters. And so in this case, you have to remember that if this object is moving far from the surface of the Earth, its mass does not change, but its weight will change, because the weight is mass multiplied by g. And if g changes, then obviously w will change, so the weight will change. However, the mass of an object remains all the time the same, as we have said earlier. The mass of an object, it's constant, it's a property, it's intrinsic property of any object, and it does not change because of any condition. Okay. This is what concerns the weight. Now let's move about the contact forces. As we have said earlier, we have two types of forces, and one type is a contact force. So contact forces act between objects that are in contact. And for any two objects in contact, we can define two components for the contact force. So we have two types of contact force. First of all, we have one that is acting along the normal to the contact force that we call the normal force. So it's perpendicular to the contact surface. And we have a second contact force that is acting parallel to the contact surface, which we call the frictional force. Okay, so you have to remember this. You have to remember that the normal force is the force that is actually acting on the normal, along the normal to the contact surface. And the frictional force is the one that is acting along the parallel to the contact surface. Pardon, the contact surface. Okay, so this is an example. Okay, so example, just imagine that you have an object that is pressing along or pressing against a surface. Like you have a table and you have a block on top of it. So the block is pressing against the surface. Okay, so the surface could deform and push the body with a normal force perpendicular to the contact surface. So the block is actually making a force, is actually pressuring this contact surface, which is the table. So this is the action. As a reaction, okay, we will have normal force acting by or exerted by the table on the block itself. And so this is the normal force that we are talking about in this case. This is the normal component of a force. For example, let's take this as an example. If we apply Newton's second law on this block, resting on the table, so it is not moving, we can say that the summation of Fy is equal to MAy. And since it's resting on the table, MAy is equal to 0. So then we end up with plus and minus mg equals to 0, and so n is equal to mg. So in this case, the normal force acting on the block by the surface, which is the table, is nothing else than the weight. The second type of contact force or component of contact force is what we call the frictional force. So for example, look at this figure here. If we slide or attempt to slide an object over a given surface, the motion is resisted by a bonding between the object and the surface. So that's what we call the frictional force, is this force that opposes the motion or attempt to move an object. But we will discuss this in detail in the future slides. Another type also of motion of force that we are going to see frequently in our chapters and discussions is the tension. So what we call the tension is the force exerted by a rope or a cable attached to an object. So here you have different examples. If you have, for example, a block attached to a cable and you pull this, you take this cable and then you just push it or pull it, whatever the direction is, you are actually applying a force on this cable, and so this cable in turn will apply a force on you or on the block, for example, and it will be pushing it in one direction or in the other, depends on the cases. So if we assume that the rope, it has negligible mass, which is all the time the case in our problems, compared to the mass of the object it pulls, and if it does not stretch, so it's inelastic or inextensible, then the tension force has the following characteristics. It's always directed along the rope, as you can see in all the examples in here. It's all the time pulling the object, and it has the same value along the rope. Okay, so this force that is inside the rope, it's always parallel to the rope, it's along the rope itself. It's all the time pulling the object. So if you look here at the block, it's pulling the block. At the hand, it's pulling the hand. Everywhere you can see the same. And it has the same value along the rope. So wherever you push from one side and the block, for example, is pushed on the other side, you are pulling the cord here, and the cord is pulling the block in here. The force is the same. T is everywhere the same. And this is thanks to the assumption that we have done, that the rope has negligible mass and does not stretch. Finally, let's go to the Newton's third law. So Newton's third law is quite important, although we do not see it, we do not discuss it and use it extensively. When two objects interact by exerting forces on each other, the forces are equal in magnitude and opposite in direction. So whenever you have two objects that are interacting, okay, object 1 and 2, they are interacting, then both of these objects, they are exerting forces on each other, and these forces, they are equal in magnitude and opposite in direction. Just take this example. You have a book that is leaning against a bookcase. Okay, so you have a crate C and the book B. The book B, the B is exerting a force on the C, on the crate. So you see, this is the force FCB. So this is the force exerted by the book on the crate. So that's why it is in this direction. And actually, in the opposite direction, the crate C will apply and will exert a force on the book B in this direction. So in the opposite direction with FCB, okay? And the Newton's third law states that FCB is equal to minus FBC. So you see from this equation that these forces, they are opposite in direction, but they are equal in magnitude. For example, one application of Newton's third law is the gravitational force itself. So you see, we have seen already this picture before. So FOE is the force exerted by the Earth on the object that we have here, right? So this is the force exerted by the Earth on the object, and in reaction, the object also exerts a force on the Earth. Of course, we don't talk about, but because we don't study the Earth as an object. But if you want to study the Earth as our object, we have to consider that this Earth is in interaction with whatever objects located around of it, and all these objects, they exert a force on the Earth by pulling it. So the Newton's third law, it states that FOE is equal to minus FEO. So the force exerted by the Earth on the object is equal to the force exerted by the object on the Earth, of course with a minus sign because they are opposite in direction. So an alternative statement of the Newton's third law. This action reaction, we call this force F1 and F2 as action reaction pair. Okay, so the action force is equal to in magnitude to the reaction force and opposite in direction. So we say that FOE, for example, here and FEO, they are action reaction pair. The same way we can say that FBC and FCB also they are action reaction pair. Now, who is the action and who is the reaction? Well, it doesn't matter. One of the forces is the action and the other is the reaction. It doesn't matter which one is the action or which one is the reaction. So it doesn't matter which is considered the action and reaction. And you have to remember that the action and so the action and the reaction forces, they act on different objects and they must be of the same type. So you cannot have an action and reaction forces acting on the same objects, because by definition, these forces, they are the forces acting between two objects. And so they have to be on the same type. Like, for example, they could be gravitational force, it could be electric force, magnetic force, nuclear force, etc. But you cannot have a reaction which is or an action which is the gravitational force and a reaction which is an electromagnetic force. They should be of the same type. Few words about the inertial frame. So actually, any reference frame in which Newton's three laws of motion are valid is defined as inertial. And the reference frame in which Newton's laws are not obeyed are labeled non-inertial. So for example, the Earth is a frame, it's a system that is rotating about its axis once every 24 hours. And thus it is accelerating with respect to an inertial, with a given inertial reference frame. But we can make an approximation, actually, when we consider the Earth to be an inertial reference frame. And this approximation is excellent for most small-scale phenomena. So in all our phenomena that we are studying, the approximation that the Earth is by itself an inertial frame is correct, because actually the Newton's law, they are valid in this inertial frame. And what you need to know is that if you have a given inertial frame R, where Newton's law are valid, and you take any other frame R prime, which is moving at constant velocity with respect to R, then this frame will be also an inertial frame. However, if you take, if you take a reference R prime that is moving with not with a given acceleration, let's say with respect to the R, then it's not going to be inertial frame. So we are not going to deal very much with this inertial frame. What you need to know is that an inertial frame is a system of reference associated to a given physical object where the Newton's law are valid and could be applied. That's it. This is the takeaway message from the inertial frames. Okay, I'll drop in here. So just here you can find a few examples, how to apply Newton's law in general. So first of all, you have to choose the study. You have to choose the system to study. You have to draw a free body diagram. So what we call a free body diagram is what you see here in part B. So for example, let's take this example of a person pulling a crate or a box. What do we have as object? So you have the weight of the box. So the box is represented by 1 point, a dot, in this free body diagram. You have a dot, and you have the gravitational force here. You have the weight of the object. You have the normal force, which is the force exerted by the surface on the block, on this box. And you have the tension in the cord, because this person is pulling this box by pulling the cord. So that's why you have a tension that is acting in the same direction as the motion. Okay. Or as well, the same direction as that applied by the person to pull the box. So this is step number 2. The system is our box. The free body diagram is drawn here. Then you have to choose the axis, a given system of reference x and y. So conventionally, we take x to the left and y upward. Then you have to identify all the forces that act on the system, and be careful not to include the forces that acting on objects not included in the system. Okay, so for example, if you take here the system to be the person and the box, then this tension would be an internal force to the system. While if you take the box alone, this T would be an external force acting on the system, which is the box in this case. So it depends on which is your system. Then you apply Newton's laws, and most of the time we're going to apply Newton's second law to find the acceleration and how the object is moving. Here you have an example of a given lamp. It's suspended from the ceiling. So you have two forces acting on this object, the weight and the tension. If the object, as we have seen here, it's in equilibrium, so it's actually, it has no acceleration. Its acceleration is simply 0. It's at rest. Then we can simply write down plus t minus fg is equal to 0, given that we have taken the y-axis upward, and so we end up with t equals to fg. Here another example that we have just considered before. So you could see that if you apply Newton's second law on this example, we will end up with two equations. The first one along the x-axis, the second one is along the y-axis. So along the x-axis, only t is acting. So we can say t is equal to max. And along the y-axis, we have plus and minus fg. It's equal to 0 because ay is equal to 0, for the reason that the box is not moving along the y-axis, but it's only moving along the x-axis. And so we end up with n equals to ft. So those are very simple examples of on how to apply Newton's laws of motion. So what about the forces of friction now? The forces of friction, it describes the frictional force between two objects. So this is actually the second component of a contact force. And you have to differentiate in this case between the static and kinetic friction. So that's what we are going to study in here. We're going to study the properties of friction. Let's do it actually. In order to introduce this, let's take this simple example, okay? Let's explore the basic properties of friction by analyzing this problem. We are going to push a heavy crate resting on a floor. So this is a crate which is resting on, this is a floor in gray. It's attached to a cord somewhere in here. And we are going to try to pull this crate. So what happens? Let's start by, we are going to go through them through steps. So in the first step, the box is at rest, okay? There is no applied force. So we have the normal force and the weight, which actually counterbalance each other. Let's now try to pull this crate horizontally. What happens? If we try to pull it, then we are applying a given force in here. Through the cable, it's the tension, it's called the tension. So we pull it, but what happens is that the box does not move. Okay, if the box does not move, that means there should be a second force, you know. If T is pulling the object to the right, then there should be another force which is acting on the box itself, on the crate, but in the other direction with respect to T to counteract the force T. Okay, so here we can deduce that this force, we are going to call it static frictional force. Why is it static? Because the object is still not moving. It's still at rest somehow. although we are applying a force T and we are trying to pull it, it's not yet moving. So that's why we call it static frictional force. And if you apply Newton's law, we will see that this Fs is equal to T. So the magnitude of Fs is equal to the magnitude of the tension in the rope. However, it has a different direction, which is just the opposite with respect to T. Now, let's actually try to pull even harder. So we are going to increase the intensity of this tension force in the cable, but still we observe that the box is not moving. So that means that as long as we have increased the tension force in the cable, then this Fs has increased as well in such a way that Fs is still equal to T, and so the box is not moving. So Fs, we can conclude that this frictional force that we have introduced in step number 2, which is opposite in direction of the tension, it increases in magnitude such that Fs and T still balance each other and the box is still not moving. Let's push even harder. Then let's push to the maximum with our strength. Then we see that the box will start to slide. So at this point, we can say that there is a maximum value for Fs, definitely, because if we were increasing the tension T, Fs is increasing. If we there should be some maximum value for Fs, so that if we exceed this maximum value, the block will start to move. Okay. And when the block starts to move, then we say that we are not any longer in the case of static friction, because the block is not at rest, but it is moving. So we talk about kinetic friction, so the force of kinetic friction, and it's denoted by Fk. Okay. So باختصار شديد بعد مرة بأول ستيب البلوك واقف محله، فإذا ما في عنا بس two forces acting on it، الويت والنورمال بيعادلوا بعضهم. لما بنيجي بدنا نشده شوي لهالبوكس ب given tension من خلال الحبل بنشده، فنحن عمليا عم نطبق عليه a given force T. اللي بنلاحظه انه هالبوكس بقي محله، طالما بقي محله معناتها لازم يكون في فورس ثانيه عم بتعادل الفورس تي، يعني عندنا نفس قيمتها بس بالاتجاه المعاكس لها، بشكل انه البوكس عم يبقى محله واقف. حنسمي هيدي الفورس static frictional force. A frictional force because it's the force ناتجة عن الكونتاكت ما بين البوكس وما بين السيرفس. سميناها static لانه البوكس بعده واقف محله ما عم يحرك. وبنستنتج من هالاكسبيرينس انه هالفورس اف اس هي equals للتي وعندها opposite direction with respect to t. In step number 3 بنشد بعد اكثر، من اول فورس اللي عم نعملها على البوكس، وبالتالي يعني هذا الشيء بيعني انه التي عم تكبر، بس بنلاحظ انه البوكس ما زال ما واقف محله ما عم يتحرك. فهذا الشيء بنستنتج من خلاله من هالاكسبيرينس انه الفورس اف اس بتقدر تكبر in magnitude بشكل انه تضلنا عم بتعادل التي اللي نحن عم نطبقها على البوكس من ثاني جهه. So Fs is acting in opposite direction with respect to T. It has the same magnitude وكمان بتقدر تكبر in magnitude. بنضلنا نشد لحد ما بالاخير نحركه للبوكس. فمن خلال هالستيب 4 بنقدر نستنتج انه actually there should be لازم يكون في maximum value of Fs. بنضلنا نشد لنوصل لهالماكسيمم فاليو. اذا وقفنا عليها بنكون البوكس بده يبلش يتحرك، اما اذا تخطيناها فبكون البوكس اوريدي تحرك، وبالتالي بنبطل بحاله ستاتيك فريكشن وانا بننتقل لحاله كاينتيك فريكشن. كاينتيك لانه الاوبجكت اوريدي بلش يتحرك. So إذا بدكم هون we can see the magnitude of a frictional force as a function of time. هون رح نحط كل الستبس اللي مرقنا فيهم على هيدا الكيرف. So لما البوكس كان at rest we were at this point where there is no force applied at all, and so there is no friction at all. There is no friction force. Fs is equal to 0. Now let's go to the case where when we started pulling the box. لما بلشنا نشده للبوكس بلشنا نكبر التي نحن. So من الناحية الثانية كانت الاف اس كمان عم تكبر. بقينا نشد والاف اس تكبر، نشد والاف اس تكبر لحد ما وصلنا لنقطة صارت الاف اس فيها ماكسيمم. لما صارت الاف اس ماكسيمم البوكس السيرفس ما بقى قادرة تعمل فريكشن أكثر من هيك على ما بقى قدرت قاوم محاولتنا انه نشده للبوكس لانه وصلت للماكسيموم. فبهالحاله بنقول انه الاف اس هي ايكوالز للاف اس ماكسيموم. وبعدين بس نتخطى هالفاليو للاف اس ماكسيمم ساعتها ندخل بالفيز انه البوكس بلش يتحرك. فبس البوكس بلش يتحرك بنصير نحكي عن كاينتيك فريكشن اف كي. ولاحظوا هون انه الفريكشن فورس لما تكون ستاتيك بكون عندها زيرو، بتكبر 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 لجيفن ماكسيمم. بمجرد ما البوكس يتحرك ترجع بتقشط على فاليو اوطى، وبعدين ببطل فيه كثير فاريشن، بتكون تقريبا كونستنت. من وقت اللي بتبلش تتحرك فيه البوكس onward بتصير عندنا instead of static friction kinetic friction, and it is approximately constant. So just a few properties about the friction force that you need to know. So when an object is in motion on a given surface, you know, also even through a viscous medium, there is a resistance, you know, to the motion of the object by the medium or by the surface. And this force, what we call the friction force F. And F friction force is always denoted by lowercase f. The force of friction, first of all, it is of two types, static and kinetic. It can be static and immediately change to kinetic whenever the object starts to move. Number two, it acts parallel to the surfaces of contact. So if you have two objects, whether it's horizontal or vertical. So on the previous example, it was horizontal, but it could be also as well vertical. But all the time, it is parallel to the surface of contact. It opposes the direction of motion in the case of kinetic friction, or actually any attempted motion in the case of static friction. So which means that نحن لما نكون عم نشد يكون في attempt للموشن، نحن عم نحاول محاولة انه يصير في موشن. فبهالحالة لما يكون في محاولة انه نعمل موشن بس الاوبجكت بعده ما عم يتحرك، بنكون عم نحكي عن static friction. لما الاوبجكت يبلش يتحرك بنصير ننتقل للكاينتيك فريكشن. بس بالحالتين the friction force, it opposes the direction in which the motion is happening or the motion will happen. Number four, the friction force is independent of the area of contact. So it does not matter how much is big or small the area of contact between the two objects. The point is that these two objects, they are in contact. It is independent of the speed of the moving object in the case of kinetic friction, which means that the magnitude of this friction force does not depend on the value of the speed of the object. It only depends on the nature of the surfaces in contact. So the only thing that differs from one case to another, why the friction force is higher or smaller, is basically the nature of the surfaces in contact, whether it's wood, metal, whatever else, okay? Water, etc. And it is proportional to the normal force. So we can always write down that the frictional force is proportional to N, where N is the normal force exerted by the surface on the object, and this N, which is perpendicular to the surface of contact. So here you can see that the two components of the contact force, the normal and the friction, they are proportional with a given factor of proportionality, which is actually we call the coefficient of friction. So let's discuss this. For the static friction, if the two surfaces do not move relative to each other, then the static friction Fs balances the applied force. And in this case, the object, let's say the object on the surface is not moving. However, the magnitude of S is not constant, as we have seen. It could change. And actually, we can write down Fs to have a limit between 0 and a maximum value. 0 when there is no attempt to move the object, and Fs maximum is when we pull at the maximum from our side and the surface is not able anymore to resist this intensity by which we are pulling the object. So it goes up to a maximum value, and only this maximum value is equal to mu s times n, where mu s is the coefficient of static friction and n is the normal force exerted by the surface. If the applied force exceeds Fs maximum, then the box starts to slide and we are in the case of kinetic friction. So once the box starts to move, the kinetic frictional force will be applied, will be acting on the object, and it's denoted by Fk. Fk is constant. It's not like Fs. Fs, it could vary from 0 to some maximum value, but Fs is always constant, and it's given by mu k times n, where mu k is known as the coefficient of kinetic friction. So what you should need to take away message is the following. So the static friction force, it has a range between 0 and a maximum value, which is equal to mu s times n, and the kinetic friction force is defined this way: Ffk is equal to mu k times n, where n is the normal force. You have to know, of course, that mu s is known as the coefficient of static friction, and you have to know that mu k is the coefficient of kinetic friction. Oh, okay. So mu k is known as the coefficient of kinetic friction. And actually, you have just to know that Fk is smaller than Fs maximum. So this observation is just an observation. Experimentally, we have seen that Fk, usually the kinetic friction, is all the time smaller than Fs maximum. That's it. Here, just some some examples about the coefficient of frictions. So, for example, here you have the different type of contacts between different surfaces. And here you have the coefficient of friction for the case of static and kinetic friction. So, for example, rubber on concrete, mu s is equal to 1, mu k is equal to 0.8, steel on steel, glass on glass, copper on steel, wood on wood, etc. So you have different cases, but you could see that in general, the coefficient of static friction and the coefficient of kinetic friction, they are all the time smaller and at maximum equals 1. But the coefficient of friction, they cannot be greater than 1. So this is all about the chapter 5 about the laws of motion. Very quickly take away messages from this presentation. You have to take away the following messages. So the Newton's first law, you have to know what it is. Then you have to know what are the contact forces, and you have to keep in mind, so this is the Newton's second law. Take away messages: sum of external forces is equal to ma. That's all what you have to know from Newton's second law. This equation is also a takeaway message. Whenever you have a problem, a system that we are dealing with, and you apply on it Newton's second law, you have to define the XYZ system and then make the projection upon X, Y, and Z axis. So don't forget that Newton's second law, it has 3 equations inside of it, which correspond to the X, Y, and Z axis projections. You have to know also, you have to memorize that the weight is given by W. W is equal to mg. And you have to remember that the mass of an object does not change, whatever changes with the object. You have to also know that the contact force is made of 2 components: the normal force denoted by N, and the frictional force denoted by F, which we have seen later in the slides. You have to check this again slide. This is the rule that we have. This is the procedure of how to solve the problem. Again, I will repeat it once. So first of all, you have to choose the system to be studied, whether, for example, in this case, is it the box? Is it the box with the surface, the box with the cable and the person, etc.? You have different choices. Once you choose your system, you have to define the free body diagram. Then you have to choose the axis, to enter all the forces that are acting on the system into this axis, and so to make the projections. Be careful not to include forces acting on objects which are not included in your system, and then you have to apply Newton's law on the system. So that's it for this chapter. After that, we are going to start with the problems.